America built heavy fighters optimized for pilot survivability and combat effectiveness, without significant resource constraints. The Corsair, the Hellcat, and the Thunderbolt achieved overwhelming capabilities by solving every problem through application of superior materials, abundant power, and robust construction. These were expensive aircraft, consuming resources in quantities Japan simply did not possess, but they kept pilots alive and won battles through systematic application of material advantage. The production statistics illustrated the impossible arithmetic Japan faced. Vought, along with Goodyear and Brewster, produced over 12,500 Corsairs between 1942 and 1952. Peak production reached approximately 300 aircraft per month in 1944. Each Corsair required thousands of man-hours of skilled labor, tons of aluminum and steel, hundreds of precision components, and one R2800 engine. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. American industry manufactured 125,000 R2800 engines by war's end, production of a single engine type exceeding Japan's entire combat aircraft engine output. When combined with Hellcat, Thunderbolt, Mustang, and other fighter production, American industry built approximately 70,000 fighters during World War II. Japan produced approximately 40,000 aircraft of all types at peak output, including trainers, transports, and obsolescent types maintained in service because nothing better was available. The production differential reflected not a failure of Japanese engineering, but rather the mathematical reality of industrial capacity measured in steel production, aluminum output, machine tool availability, skilled workforce size, and factory capacity. Japanese engineers examining the captured Corsair understood these implications with painful clarity. Their technical reports documented not just an aircraft's capabilities, but the dimensions of a technological and industrial gap that could not be closed through clever design or superior tactics. The Americans had not won through better engineering in the abstract sense. They had won through the ability to implement good engineering at industrial scales that overwhelmed opponents with fewer resources. The 2,000 horsepower R2800 engine represented the physical manifestation of this advantage. It was not an experimental engine produced in limited numbers for special purposes. It was standard equipment, installed in thousands of aircraft, supported by logistics networks that delivered fuel, spare parts, and replacement engines anywhere American forces operated. Japanese pilots facing Corsairs in combat were not fighting superior technology in isolation. They were fighting an integrated system of aircraft, engines, fuel, ammunition, spare parts, maintenance infrastructure, pilot training, and tactical doctrine, all supported by industrial capacity operating at scales Japan could observe but never match. The psychological impact on Japanese forces of facing endless streams of capable American aircraft proved as destructive as the material losses. Japanese pilots reported feeling less like warriors in honorable combat and more like targets in a systematic destruction campaign. No matter how many American aircraft they shot down, more appeared the next day. No matter how skillfully they fought, American numerical superiority eventually prevailed through attrition that Japan could not sustain. The knowledge that American equipment was often superior to Japanese designs, delivered in far greater quantities, supported by better logistics, and flown by adequately trained pilots who were quickly replaced when lost, created a pervasive sense of inevitable defeat that spread throughout Japanese military aviation during 1944 and 1945. The captured Corsairs served as tangible physical evidence of this reality. These were not propaganda claims or exaggerated intelligence reports. They were actual aircraft that Japanese pilots could examine directly. The F4U Corsair's combat record in the Pacific validated everything Japanese engineers had learned from their examination. Marine and Navy Corsair squadrons compiled an 11-to-1 kill ratio during World War II, destroying over 2,140 Japanese aircraft in aerial combat, while losing only 189 Corsairs to enemy fighters. This ratio reflected the combined impact of superior aircraft performance, sound tactical doctrine, increasingly skilled American pilots, and declining Japanese opposition as experienced aviators were killed and inadequately trained replacements were thrown into combat. The Battle of Okinawa in the spring of 1945 demonstrated the Corsair operating at peak effectiveness. Corsair squadrons provided the primary defense against Japanese kamikaze attacks, intercepting suicide aircraft before they could reach American ships. On April 22, 1945, Corsair pilots from Marine Fighting Squadron 323 engaged a formation of 80 kamikazes, attacking picket ships north of Okinawa at dusk. The Marines shot down 23 attackers in minutes, with 3 pilots, including the squadron commander, downing 5 or more aircraft each. The battle was fought under low clouds, with rain showers obscuring visibility, conditions that favored neither side, but that the well-trained American pilots handled with discipline and coordination. During their combat tour at Okinawa, the squadron was credited with 124.5 Japanese aircraft destroyed, most of them kamikazes. The Corsair's speed allowed rapid interception, its climb rate enabled engagement at optimal altitude, its firepower destroyed fragile Japanese aircraft with short bursts, and its robust structure absorbed return fire and battle damage. Japanese High Command recognized the Corsair's effectiveness through bitter experience. Post-war interrogations of senior Japanese officers revealed that they considered the Corsair among the most formidable American fighters, a view shared by Japanese pilots who survived combat against the distinctive gull-winged fighters. The aircraft's reputation among Japanese aviators evolved from professional respect in 1943 to wary caution in 1944 to outright fear by 1945, as losses mounted and the strategic situation became hopeless. The story of Japan's captured Corsairs thus becomes a microcosm of the Pacific War's broader narrative. Japanese engineers could examine American equipment, understand American capabilities, and accurately assess American industrial strength. This knowledge was professionally gathered, carefully analyzed, and thoroughly documented in technical reports distributed through military channels. But knowledge alone could not overcome the material realities that determined the war's outcome. Understanding that the R-2800 engine produced 2,000 horsepower did not provide Japan with the high-grade steel alloys, precision machine tools, skilled machinists, and undamaged factories needed to build equivalent engines at scale. Recognizing that American fighters carried comprehensive armor protection did not grant Japan access to the armor plate, specialized rubber compounds for self-sealing tanks, and manufacturing capacity to equip its fighters equivalently while maintaining production rates. Documenting the Corsair's superior performance characteristics did not change the mathematics of attrition warfare when America produced 12,000 Corsairs while simultaneously building 15,000 Hellcats, 15,000 Thunderbolts, and thousands of other combat aircraft. The knowledge arrived too late and proved too vast to matter strategically. By the time Hammond's Corsair was being examined at Yokosuka in the spring of 1945, the outcome of the war had already been determined by industrial arithmetic that no amount of Japanese engineering skill or pilot courage could overcome. The final irony was that Japanese engineers learned their lessons thoroughly, documented them professionally, and grasped the implications completely, yet could never apply the knowledge gained. Understanding American industrial superiority did not grant Japan the resources to compete. Knowing the Corsair's exact capabilities did not provide the fuel to properly test captured examples or train pilots to counter American tactics. Intelligence gathered from captured aircraft documented the dimensions of Japanese defeat with technical precision without offering any realistic path to avoid that defeat. The captured Corsairs ended their service in the chaotic final weeks of the Pacific War. When American occupation forces arrived in Japan after the surrender in August 1945, they discovered the repaired fighter at Kasumigara, still wearing improvised fabric patches and Japanese identification markings hastily painted over American stars. Photographs taken by American intelligence teams show the aircraft parked among Japanese trainers and obsolescent fighters, a physical reminder of the technological gap that had widened steadily from Pearl Harbor through Midway to the Philippines and finally to the home islands themselves. The Corsair was evaluated briefly by American technical intelligence officers, curious about Japanese restoration methods and analysis procedures. The fabric patches and improvised repairs told their own story about Japanese resourcefulness working under impossible material constraints. The careful documentation and professional engineering analysis, evident in Japanese technical reports, impressed American evaluators who recognized the thoroughness and competence with which their opponents had studied captured equipment throughout the war. But the captured Corsair's ultimate fate was anticlimactic. With no historical preservation value beyond documentation already completed, the aircraft was eventually scrapped, its aluminum recycled, its components dispersed. The engineering knowledge Japanese technicians had gained from months of examination disappeared into archived reports that would gather dust in military files for decades before historians rediscovered them and recognized their significance as primary source documentation of how Japan had confronted its industrial inferiority. The human stories behind the captured aircraft provide sobering counterpoint to the technical narrative. Lieutenant Hammond survived his captivity, enduring harsh conditions in Japanese prisoner-of-war camps until liberation in August 1945. He returned to the United States, eventually learning that his Corsair had provided enemy engineers with detailed intelligence during the war's final months. The knowledge troubled him less than might be expected. By February 1945, when he made his emergency landing, the war's outcome was no longer in doubt. The Corsair examination had documented Japanese defeat rather than enabled Japanese victory. The Japanese engineers who examined the captured Corsairs faced their own reckoning with defeat. Many had devoted their careers to naval aviation, designing aircraft and engines for the Imperial Navy with skill and dedication. They had created fighters like the Zero that dominated early war combat through clever optimization within severe constraints. They had attempted to compete with opponents possessing vastly greater resources through superior design philosophy and efficient engineering. But by 1945, they confronted the reality that efficiency and cleverness could not overcome abundance and power when applied at industrial scales. The Corsair examination had taught them lessons they already understood, but had hoped to deny. American victory was inevitable, not because American engineers were more skilled, but because American industry could implement adequate engineering at production scales Japanese factories could never approach. The post-war period brought different lessons. Japanese engineers, many of them veterans of wartime aviation programs, would apply their skills to rebuilding their nation's industrial base. The efficiency and optimization techniques that had characterized wartime Japanese fighter design would find new expression in post-war manufacturing that emphasized quality, precision, and continuous improvement. But that story lay in the future. In the spring of 1945, as Japanese engineers documented the captured Corsairs' capabilities, they were recording the final chapter of Imperial Japan's attempt to compete militarily with American industrial power. The broader historical significance of the captured Corsair examination extends beyond documenting Japanese defeat. The episode illuminates fundamental truths about modern industrial warfare that remain relevant decades later. Victory in conflicts between industrialized nations depends less on tactical excellence or individual technological breakthroughs than on the ability to produce adequate weapons in overwhelming quantities while sustaining complex logistics, networks that keep forces supplied and operational. The Corsair succeeded not because it was the absolute best possible fighter aircraft by every conceivable measure, but because it was a very effective fighter produced in quantities that made isolated examples of Japanese technical excellence strategically irrelevant. American industry built 12,500 Corsairs, while simultaneously producing comparable numbers of other fighter types, bombers, transports, and training aircraft. Each aircraft represented thousands of hours of labor, tons of strategic materials, hundreds of precision components, and manufacturing capacity that exceeded Japan's entire industrial base. The 2,000 horsepower R2800 engine symbolized this material abundance transformed into military capability. It was powerful, reliable, and manufactured in quantities exceeding 125,000 units. More engines of this single type were produced than Japan manufactured combat aircraft engines of all types combined. The statistic illustrates not Japanese industrial failure, but rather the scale of American industrial capacity operating without the constraints that limited Japanese production. The lesson Japanese engineers learned from examining the captured Corsair was ultimately a lesson about industrial capacity as a strategic weapon. Technology matters, design philosophy matters, pilot skill matters. But when one combatant can produce 5 times as many aircraft, powered by engines with 40% more power, supported by logistics networks that deliver unlimited fuel and spare parts, crewed by adequately trained pilots who are rapidly replaced when lost, the outcome becomes mathematically inevitable, regardless of tactical skill or fighting spirit. This recognition did not represent Japanese defeatism or lack of courage. It represented professional assessment of material reality by engineers who understood their field thoroughly. They could measure the Corsair's 2,000 horsepower and compare it to their best engine's 1,500 horsepower. They could weigh the aircraft's armor protection and compare it to the minimal armor on Japanese fighters. They could examine manufacturing quality and recognize precision their own factories could no longer achieve. The evidence was physical, measurable, and undeniable. The captured Corsair's final contribution to history was thus not tactical intelligence that changed battle outcomes, but rather documentation that helps historians understand how industrial capacity determines modern warfare results. The aircraft served as a physical manifestation of American industrial philosophy applied to military aviation. Build it tough, protect the pilot, install the most powerful engine available, arm it heavily, accept weight penalties as manageable problems, and produce enough of them to overwhelm opposition through systematic application of material superiority. This approach succeeded not through genius, but through the systematic implementation of adequate solutions at scales that rendered Japanese qualitative advantages insufficient. Japanese fighters were lighter, more maneuverable at low speeds, and longer-ranged than American equivalents in early war years. These advantages mattered during the conflict's first 18 months, when American production had not yet reached full capacity, and American pilots lacked combat experience. But as American industry mobilized, trained millions of workers, built thousands of factories, and refined production processes, the quantitative advantages became overwhelming. By 1945, Japanese pilots faced opponents who held every advantage. American pilots flew faster aircraft with better climb rates, heavier firepower, superior protection, and adequate, if not exceptional, maneuverability. American pilots received longer, more comprehensive training that produced competent aviators in industrial quantities. American squadrons operated from bases supplied by logistics networks that never failed to deliver fuel, ammunition, and spare parts. American tactical doctrine emphasized mutual support and disciplined execution over individual heroics. The mathematical result was inevitable. Japanese aviation was not defeated by superior tactics or revolutionary technology. It was ground down by systematic attrition that Japan could not sustain. Every engagement cost irreplaceable pilots and aircraft, while American losses were quickly replaced from training programs producing thousands of new aviators annually and factories, delivering hundreds of new aircraft monthly. The captured Corsair examination documented this reality with engineering precision, measuring the physical dimensions of a military defeat determined by industrial capacity operating at national scale. The story concludes where it began, with Lieutenant Hammond's emergency landing on February 25, 1945, at Tsuchiura Airfield. That single forced landing delivered to Japanese engineers a complete operational example of American naval aviation's finest fighter at the moment when such intelligence could be most thoroughly analyzed but least effectively applied. The examination revealed truths Japanese high command had desperately hoped to deny, but which frontline pilots had reported for 2 years. American equipment was superior across most categories, produced in overwhelming quantities, and supported by industrial capacity Japan could never match. The Corsair sitting in that Yokosuka hangar, surrounded by Japanese engineers documenting every component and system, represented more than one captured aircraft. It symbolized the transformation of American industrial capacity into military power that had systematically dismantled Japanese control of the Western Pacific through the application of material abundance at unprecedented scale. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The examination taught lessons thoroughly, documented them professionally, and transmitted them through military channels where they joined accumulating evidence that the war was lost and continued resistance merely delayed inevitable defeat while consuming lives to no strategic purpose. In the end, the captured Corsair served as both intelligence prize and historical artifact, providing Japanese engineers with detailed knowledge of American technology, while simultaneously documenting for future historians the industrial foundations of American victory in the Pacific War. The aircraft has long since been scrapped, its aluminum recycled, its components dispersed, but the technical reports compiled by Japanese engineers survive in archives, testament to professional competence, analyzing an opponent's capabilities, even as defeat became undeniable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. February 25th, 1945. Tsuchiura Airfield, Ibaraki Prefecture, Japan. The massive gull-winged fighter dropped from the low clouds, trailing smoke from its Pratt & Whitney R-2800 engine. Lieutenant Junior Grade Robert Hammond of Bomber Fighting Squadron 85, USS Essex, had been over Tokyo Bay minutes earlier, his Corsairs 18 cylinders roaring at full war emergency power as he evaded Japanese anti-aircraft fire during strikes against enemy shipping. Now the oil pressure gauge read 0, the temperature climbed past redline, and the choice before him narrowed to a single impossible option: bail out over the freezing waters of Sagami Bay or attempt an emergency landing on what appeared to be an open field below. Hammond chose the field. The F4U-1D, Bureau number 57251, touched down hard on the grass airstrip, its massive 13-foot four-blade propeller still windmilling as the dying engine seized. The fighter rolled perhaps 200 yards before stopping, surrounded immediately by Japanese soldiers who had watched its descent with a mixture of alarm and opportunistic excitement. Hammond climbed from the cockpit, hands raised, his war as a naval aviator over at age 23. But for the Imperial Japanese Navy's engineers at the nearby Yokosuka Naval Air Technical Arsenal, an education was about to begin that would fundamentally alter their understanding of American industrial capacity and the technological chasm that now separated Japan from its opponent. What they discovered when they examined this single captured aircraft would confirm what Japanese High Command had desperately hoped to deny. America had not simply matched Japan's engineering excellence, they had overwhelmed it through an industrial philosophy that treated advanced technology as standard equipment rather than exceptional achievement. The story of Japan's captured Corsairs reveals how material abundance, when transformed into military hardware, renders tactical skill and pilot courage insufficient to overcome the mathematics of industrial warfare. The capture of Hammond's Corsair on February 25, 1945, was not the first time Japanese forces had encountered the distinctive gull-winged fighter in combat. Japanese pilots had been fighting Corsairs since February 1943, when Marine Corps squadrons first brought them into action over Guadalcanal. Initial combat reports from Japanese fighter units reflected professional respect tempered with growing concern. The new American fighter was faster than anything Japan fielded at medium and high altitudes, climbed with astonishing rapidity, and could absorb battle damage that would destroy a Zero. Combat accounts from Japanese pilots throughout 1943 and 1944 consistently mentioned specific characteristics that troubled them deeply. The Corsair accelerated in a dive to speeds no Japanese fighter could match. Its 650 caliber machine guns fired with devastating concentration, capable of shredding a Zero's lightweight airframe with a single well-aimed burst. Most disturbing, damaged Corsairs routinely continued flying, limping back to their carriers or island bases with battle damage that should have been fatal. Japanese intelligence officers collecting pilot debriefs noted a pattern that contradicted the narrative of American technical inferiority that had sustained Japanese confidence through the early war years, where Japanese fighters traded protection for performance, building aircraft that were fast and maneuverable but fragile. The Corsair appeared to offer both. It was fast, it climbed well, it turned adequately for its size, and it survived hits that would kill a Japanese pilot instantly. The Imperial Japanese Navy maintained two principal facilities for analyzing captured enemy equipment. The Army operated the Aviation Technical Research Institute at Tachikawa Airfield, northwest of Tokyo, while the Navy's first air technical arsenal operated from Yokosuka Naval Base, approximately 50 miles southwest of Tokyo, on the western shore of Tokyo Bay. Both facilities had been examining captured Allied aircraft since the war's beginning, attempting to identify weaknesses that could be exploited tactically and technologies that might be replicated in Japanese designs. But by early 1945, the strategic situation had deteriorated to the point where captured aircraft analysis served less to identify exploitable weaknesses and more to document the dimensions of Japan's industrial inferiority. American bombing raids had crippled Japanese production capacity. Strategic materials were increasingly unavailable. The fuel needed to properly test captured aircraft engines at full power was scarce. The skilled technicians and engineers who might replicate American technologies were either dead, conscripted for military service, or working desperately to keep existing Japanese aircraft flying with substitute materials and improvised repairs. Into this context came Hammond's Corsair, damaged but remarkably intact, landing at a field adjacent to one of Japan's most important naval flight schools. Within hours of the emergency landing, personnel from the Yokosuka arsenal arrived to secure the aircraft and begin preliminary assessment. The fighter was immediately surrounded by armed guards to prevent civilians from approaching or damaging the valuable intelligence prize. Measurements were taken, photographs were captured from multiple angles, and arrangements were made to transport the aircraft to Yokosuka for detailed examination. Japanese technical officers conducting the initial inspection noted several details that would prove significant during later analysis. The aircraft appeared substantially larger than any single-engine fighter in Japanese service, with a wingspan of 41 feet and an overall length of 33 feet 4 inches. The distinctive inverted gull-wing configuration positioned the landing gear at the wing's lowest point, allowing shorter, lighter gear while providing ground clearance for the enormous propeller. The construction quality was immediately apparent, with flush riveting throughout the airframe and a surface finish smoother than Japanese engineers could achieve with available materials and manufacturing processes. The damage to Hammond's aircraft was substantial but localized. The engine had seized from oil starvation caused by battle damage during the Tokyo Bay raid, but the airframe itself remained structurally sound. One wing showed minor damage from ground fire, easily repairable. The cockpit instruments were intact. Most remarkably, despite the forced landing and engine failure, the aircraft appeared capable of being restored to flying condition, given sufficient time, spare parts, and expertise. A second Corsair had been captured weeks earlier under similar circumstances, also making an emergency landing rather than crashing. This second aircraft had suffered more extensive damage and would serve primarily as a source of spare parts for restoring Hammond's fighter to flyable condition. The prospect of testing an intact, operational example of America's finest carrier fighter energized the engineering staff at Yokosuka, despite the deteriorating war situation. The transportation of Hammond's Corsair from Tsuchiura to Yokosuka required careful planning and considerable effort. The fighter could not be flown, with its seized engine incapable of restart. Instead, it was partially disassembled, with wings removed and transported separately on specially constructed trucks. The journey took several days through a Japan increasingly devastated by American B-29 raids. Industrial facilities lay in ruins, transportation networks functioned sporadically, and civilian morale had reached its nadir. By early March 1945, the captured Corsair arrived at Yokosuka Arsenal, where it was moved into a secure hangar for detailed examination. The engineering team assigned to analyze the American fighter consisted of approximately 12 specialists, led by technical officers with extensive experience evaluating foreign aircraft. Many had examined captured British, American, and Soviet aircraft throughout the war, compiling detailed reports on enemy capabilities and attempting to identify technologies Japan might replicate. What distinguished this evaluation from earlier captured aircraft analysis was the context. In 1942 and 1943, Japanese engineers had examined captured P-40 Warhawks, F-4F Wildcats, and other Allied aircraft with professional curiosity and the confidence that came from early war victories. They noted strengths to be respected and weaknesses to be exploited, but fundamentally believed Japanese engineering could match or exceed American capabilities through superior design philosophy that prioritized efficiency over brute force. By 1945, that confidence had eroded under the weight of accumulated evidence. Every captured American aircraft revealed materials Japan could no longer obtain, manufacturing precision Japan could no longer achieve, and design philosophies Japan could no longer afford to implement. The Corsair evaluation would confirm what many Japanese engineers privately acknowledged, but few would state openly. Japan was not competing in the same category of industrial warfare as the United States. The examination began with systematic photography and measurement of every accessible component. Engineers documented overall dimensions, noting that the F4U 1D weighed approximately 9,200 pounds empty and could operate at gross weights exceeding 14,000 pounds when fully loaded with fuel, ammunition, and ordnance. For comparison, Japan's Mitsubishi A6M50 weighed approximately 4,300 pounds, empty and operated at maximum weights around 6,000 pounds. The weight differential was staggering, more than double the Zero's maximum weight. This single fact illuminated the fundamental philosophical divide between Japanese and American fighter design. Japan built fighters to be light, maneuverable, and long-ranged, accepting minimal protection and fragile structure as necessary compromises. America built fighters to be powerful, survivable, and capable, accepting weight penalties as manageable problems solved through larger engines and stronger structures. The Corsairs armament installation provided the first detailed lesson in American design priorities. 6 Browning M2 50-caliber machine guns were mounted in the wings, 3 per side, with each gun fed from a dedicated ammunition box built into the wing structure. Total ammunition capacity was 2,390 rounds across all 6 guns, allowing approximately 30 seconds of continuous fire at the combined rate of fire approaching 100 rounds per second. Japanese engineers carefully measured the installation, noting several details that distinguished American practice from Japanese methods. Each machine gun was mounted in an electrically heated compartment designed to prevent the weapons from freezing at high altitude, where temperatures routinely dropped below -40 degrees Fahrenheit. Spent cartridge cases and disintegrating belt links were collected through carefully designed chutes and ejected through ports in the wing's lower surface, preventing debris from damaging the aircraft or fouling control surfaces. The harmonization system allowed armorers to adjust each gun's angle, so all 6 weapons converged at a specific distance, typically between 200 and 300 yards, creating a concentrated cone of fire, devastating to any target. Japanese fighters typically carried mixed armament of machine guns and cannons with different ballistic characteristics, making harmonization more complex and reducing effective engagement range. Testing revealed that American 50-caliber ammunition was manufactured to consistently higher quality standards than Japanese equivalents. The armor-piercing rounds used hardened steel cores manufactured to precise specifications. The incendiary compounds ignited reliably. The tracer elements burned predictably, allowing pilots to walk their fire onto targets. Japanese ammunition production, degraded by material shortages and declining quality control, showed increasing inconsistency that reduced combat effectiveness. The armor protection system demonstrated American willingness to accept significant weight penalties in exchange for pilot survivability. The cockpit was surrounded by heavy armor plate, protecting the pilot from multiple angles. Behind the seat, a thick armor plate provided protection from rear attacks. The windscreen incorporated bulletproof glass, capable of stopping machine gun rounds and resisting cannon shell fragments. Additional armor plates protected critical systems, including the oil cooler and vulnerable fuel lines. Japanese engineers carefully measured the armor installation, calculating that total armor weight exceeded 200 pounds. This represented weight equivalent to adding substantial additional fuel capacity or reducing structural weight for improved performance. Japanese fighters carried minimal armor protection, prioritizing lighter weight and better performance, while accepting higher pilot casualties as an unavoidable cost of aerial combat. The philosophical difference revealed itself in the survival statistics. American pilots routinely survived being shot down, protected by armor, self-sealing fuel tanks, and robust structure. Japanese pilots died at far higher rates, their lightweight fighters offering minimal protection. The fuel system incorporated self-sealing tanks using a rubber compound that swelled when punctured by gunfire, plugging holes and preventing catastrophic fuel loss. Japanese engineers examining the technology understood the principles perfectly. They had attempted to develop similar systems, but lacked the specialized rubber compounds and manufacturing expertise to produce reliable self-sealing tanks in quantity. The Corsairs tanks represented another example of technology. Japan understood theoretically, but could not implement practically given material constraints and industrial limitations. But the Pratt & Whitney R2800 double wasp engine commanded the most intense scrutiny during the examination. This was the heart of the Corsairs' capabilities, the component that enabled all its performance advantages. Engineers approached the massive radial engine with professional curiosity, tempered by the recognition that they were examining technology fundamentally beyond current Japanese industrial capacity to replicate. The R2800 consisted of 18 cylinders arranged in 2 rows of 9 cylinders each around a central crankshaft. Total displacement measured 2,800 cubic inches, equivalent to 45.9 litres. The engine in Hammond's Corsair was an R2800-8W variant, rated at 2,000 horsepower at military power settings and capable of 2,250 horsepower, using water methanol injection for war emergency power. For direct comparison, the Nakajima Sakai engine powering the Mitsubishi A6 M0 displaced 1,702 cubic inches and produced between 950 and 1,130 horsepower depending on variant. The Mitsubishi Kasei, Japan's largest production radial engine, displaced 2,567 cubic inches and produced between 1,530 and 1,850 horsepower in various models. The Nakajima Homare, Japan's most powerful production engine and roughly comparable in layout to the R2800 with 18 cylinders in 2 rows, was designed to produce 1,900 horsepower, but reliability problems and manufacturing defects meant actual output often fell below 1,500 horsepower. The R2800 produced approximately 400 to 700 more horsepower than Japan's best engines, while demonstrating reliability that Japanese power plants increasingly failed to match as the war progressed. This performance advantage translated directly into combat capabilities. The additional power gave the Corsair superior speed, climb rate, acceleration, and the ability to sustain high-speed flight at altitudes where Japanese fighters struggled. Japanese engineers spent weeks disassembling the Corsair's engine, methodically documenting every component and system. What they discovered revealed engineering sophistication and manufacturing precision that Japan could observe and measure, but not replicate. The crankshaft was forged from high-grade steel alloy, using materials Japanese metallurgists recognized as superior to anything available in Japan by 1945. The connecting rods were machined to tolerances Japanese factories could no longer achieve consistently with worn tooling and undertrained replacement workers. The cylinder construction demonstrated advanced techniques Japanese industry had attempted, but never successfully implemented at scale. Each cylinder consisted of a machined steel barrel with cooling fins, topped by an aluminum head with sodium-cooled exhaust valves to handle extreme temperatures. The fins themselves were machined directly from solid aluminum forgings rather than cast, allowing much finer pitch and greater surface area for cooling. This technique required specialized machinery and manufacturing processes that Japanese industry lacked. The cooling fins on the R2800 cylinders were cut using automated milling equipment that precisely controlled fin depth, spacing, and contour. Japanese engineers examining the work could see that every cylinder was manufactured to identical specifications with no visible variation in quality. This level of manufacturing consistency represented a degree of quality control and process standardization that Japanese wartime production increasingly failed to achieve. The magnetos used materials that were scarce in Japan. The spark plugs incorporated high-grade ceramics superior to Japanese equivalents. The fuel injection system operated with precision Japanese engineers associated with laboratory equipment rather than combat aircraft components, expected to function reliably under harsh conditions. The valve train components showed surface finishes achievable only through precision grinding and careful quality control throughout manufacturing. Most tellingly, the entire engine showed no signs of material substitution or quality compromises forced by resource limitations. The Americans had built this engine exactly as originally designed, using all specified materials and processes with no apparent shortcuts necessitated by scarcity. This level of manufacturing fidelity to design specifications was becoming impossible for Japanese industry to achieve, as strategic bombing degraded factory capacity, skilled workers were conscripted or killed, and material shortages forced constant improvisation. The supercharger system revealed another dimension of American engineering philosophy. The R2800 used a two-stage, two-speed mechanical supercharger driven by the engine crankshaft through a sophisticated gear train. This system compressed intake air at low altitude and automatically shifted to higher boost ratios as altitude increased, maintaining engine power where normally aspirated engines would lose output dramatically as air pressure decreased. Japanese engineers understood supercharger principles thoroughly. Several Japanese engines used single-stage superchargers with reasonable effectiveness, but the two-stage system in the R2800 represented a level of mechanical complexity and precision manufacturing that Japanese industry found difficult to replicate reliably. The system required specialized high-temperature alloys for turbine components, precision gear cutting for the drivetrain, automatic controls that adjusted boost pressure based on altitude and throttle position, and an intercooler to reduce compressed air temperature. Every component had to function reliably in combat conditions, exposed to vibration, temperature extremes from -60 degrees Fahrenheit at altitude to over 200 degrees near the engine, and potential battle damage. The Americans had integrated all these elements into a compact, reliable system installed as standard equipment on every Corsair produced. For Japanese engineers, this casual implementation of advanced technology as routine production equipment revealed an industrial capacity almost incomprehensible in its scale and sophistication. The examination team also studied the propeller system, discovering another example of American technological advantage implemented through superior engineering and manufacturing. The Corsair used a Hamilton standard hydromatic propeller with a diameter of 13 feet 4 inches. The four-blade design represented optimal compromise between propeller efficiency and ground clearance constraints. The propeller pitch was controlled automatically by a constant speed governor that maintained optimal blade angle across all flight conditions, maximizing efficiency without requiring constant pilot attention. Japanese aircraft used manually controlled propellers or simpler automatic systems that were less sophisticated than American equivalents. The Hamilton Standard unit demonstrated engineering refinement and manufacturing precision that Japanese engineers could analyze, but not replicate with available resources. The hydraulic control mechanism required precision-machined components, specialized seals, and careful quality control. The propeller blades themselves were manufactured using techniques that produced lightweight, strong structures capable of handling tremendous mechanical loads. The restoration effort to return the captured Corsair to flying condition progressed slowly through March and April 1945, hampered by material shortages, the lack of proper tools and equipment, and the deteriorating strategic situation. Engineers cannibalized parts from the second captured Corsair, using its components to repair damage to Hammond's aircraft. The wing fabric patches that American forces would later note when they recaptured the aircraft in August 1945 represented improvised repairs using materials Japanese engineers had available rather than proper replacement panels they lacked. The engine restoration proved particularly challenging. Fuel shortages meant that ground testing at full power was impossible. The specialized tools required for proper timing and adjustment were unavailable. American lubricating oil, manufactured to specifications, Japanese petroleum refining could not match, was substituted with inferior Japanese equivalents that would accelerate wear and reduce reliability. Despite these limitations, the engineering team succeeded in returning the engine to operational status, achieving a remarkable feat of technical improvisation under conditions that would have defeated less skilled personnel. By late April or early May 1945, the captured Corsair was restored sufficiently for flight testing. Japanese test pilots approached the massive American fighter with respect and considerable caution. The aircraft was substantially larger and heavier than any single-seat fighter they had flown. The controls, instruments, and systems were all unfamiliar. Operating procedures had to be inferred from examination rather than learned from manuals or instruction. Most critically, the fuel situation meant that extended testing at high power settings was impossible. The test flights that were conducted revealed performance characteristics Japanese pilots had experienced from the receiving end of combat engagements, but could now measure directly. The Corsair accelerated with authority that reflected its enormous power to weight advantage over Japanese fighters. The rate of climb exceeded anything in Japanese service by substantial margins. Maximum speed at altitude approached 425 miles per hour, faster than any Japanese fighter could achieve. But what impressed Japanese test pilots most profoundly was not the raw performance, which they had expected based on combat reports, but rather the quality of engineering evident in every aspect of the aircraft's design and construction. The controls were well balanced and responsive. The cockpit layout was logical, and instruments were easily read. Visibility was excellent compared to Japanese fighters, particularly forward visibility during landing approaches that had plagued Japanese designs. The structure felt solid and robust in ways Japanese fighters did not. Stick forces were moderate, requiring neither excessive strength nor hair-trigger sensitivity. The landing gear absorbed hard touchdowns without complaint. Everything about the aircraft communicated a design philosophy that prioritized pilot effectiveness and survivability over abstract metrics of performance optimization. Technical reports compiled by Yokosuka engineers and distributed through Japanese Navy channels emphasized findings that troubled high command deeply. The document noted that engineers were surprised at the extremely strong construction upon examining the captured aircraft. When wing panels damaged by ground fire were repaired, engineers expressed amazement that some areas incorporated fabric covering over metal structures, a technique Japanese designers had used extensively but assumed Americans had abandoned in favor of all-metal construction. The fabric covering represented weight savings in non-critical areas, demonstrating that American designers understood optimization principles, but implemented them while maintaining overall structural strength far exceeding Japanese practice. The reports documented the Corsair's construction quality in detail, noting flush riveting throughout the airframe, precision-machined components, and consistent manufacturing standards across all examined parts. Japanese engineers observed that American factories produced aircraft components to tolerances Japanese industry could achieve in prototype construction, but not maintain through mass production as tooling wore, skilled workers were lost, and quality control standards degraded under pressure to increase output. Most significantly, the reports emphasized the power output of the R2800 engine, noting that the 2,000 horsepower rating exceeded anything available in Japanese service by margins that tactical skill could not overcome. The additional 400 to 700 horsepower translated into combat advantages across every performance parameter. The Corsair could choose when to engage and when to disengage, dictating the terms of combat through superior speed and climb rate. Japanese pilots, no matter how skilled or motivated, could not force engagement with opponents who held overwhelming power advantages. The strategic implications were documented with professional clarity. The reports noted that the F4U Corsair represented not an isolated example of superior engineering, but rather a systematic manifestation of American industrial philosophy. The aircraft demonstrated that America built fighters to be powerful, protective, and capable, accepting weight penalties as problems solved through larger engines and stronger structures. This approach required abundant strategic materials, sophisticated manufacturing infrastructure, and industrial capacity operating at scales Japan could not match. The Yokosuka analysis concluded that American fighters like the Corsair, the Grumman F6F Hellcat, and the Republic P-47 Thunderbolt all shared common design philosophies reflecting unlimited material resources and manufacturing capacity. They were built tough, capable of absorbing battle damage that would destroy Japanese aircraft. They protected pilots with armor and self-sealing tanks that Japanese industry could not provide in equivalent quantities. They carried heavy armament and substantial ammunition loads. Most critically, they were powered by engines producing between 2,000 and 2,800 horsepower, giving them performance advantages that rendered Japanese fighters inferior across most combat scenarios. Japanese fighter pilot training incorporated lessons from the captured Corsair analysis, though by mid-1945, the effectiveness of such training was limited by fuel shortages that reduced flight time and the decreasing skill level of replacement pilots receiving abbreviated instruction. Pilots were advised to avoid engaging Corsairs at medium and high altitudes, where the American fighter's supercharger provided decisive advantages. They were warned that diving away from pursuing Corsairs was futile, as the heavier American fighter would simply accelerate to speeds Japanese aircraft could not match. The tactical guidance emphasized that successful engagements required numerical superiority, altitude advantage, and willingness to break off combat if conditions became unfavorable. But increasingly, Japanese pilots found themselves unable to implement such tactics. American fighters operated in coordinated formations with disciplined mutual support. They maintained altitude advantage through superior climb performance. They chose engagement conditions that favored their strengths while negating Japanese advantages in low-speed maneuverability. By the summer of 1945, the strategic situation had deteriorated beyond any possibility of recovery. American carrier task forces operated with near impunity off the Japanese coast. B-29 raids had devastated urban and industrial areas across the home islands. The Imperial Navy's carrier aviation had been effectively destroyed, its experienced pilots dead, and its remaining aircraft grounded by fuel shortages. The captured Corsair at Yokosuka represented a museum piece documenting technological superiority that Japanese industry could never overcome. When American forces occupied Japan in August 1945 after the surrender, they discovered the captured Corsair at Kasumigara Naval Air Station, the flight school adjacent to where Hammond had made his emergency landing 6 months earlier. The aircraft still wore patches of fabric covering battle damage and improvised repairs, silent testimony to Japanese engineering skill working under impossible constraints. American intelligence officers examining the fighter noted the careful documentation and professional analysis Japanese engineers had conducted, recognizing the thoroughness with which their opponents had studied American technology. The captured Corsair was evaluated by American technical intelligence teams and eventually scrapped, its intelligence value exhausted. Lieutenant Hammond survived his captivity and returned to the United States after the war ended, eventually learning that his aircraft had provided Japanese engineers with detailed insights into American fighter capabilities during the final months of the Pacific War. The broader lessons from Japan's examination of captured Corsairs extend beyond the specific technical details of one aircraft type. The evaluation demonstrated how industrial capacity operating at national scale becomes the decisive factor in modern warfare when one combatant possesses overwhelming material advantages. Japan understood American technology clearly, analyzed it professionally, and documented its capabilities thoroughly. But understanding alone could not produce the aluminum, steel, rubber, specialized alloys, machine tools, skilled workers, undamaged factories, and functioning transportation networks required to compete with American industrial output. The philosophical differences between Japanese and American fighter design reflected fundamental realities about available resources and industrial capabilities. Japan built lightweight fighters optimized for performance within severe material constraints. The Zero, the Ki-43 Oscar, and other Japanese fighters achieved remarkable capabilities through clever design that maximized performance while minimizing weight and material consumption. These were excellent aircraft, given the constraints under which they were designed and the resources available for their construction. America built heavy fighters optimized for pilot survivability and combat effectiveness without significant resource constraints. The Corsair, the Hellcat, and the Thunderbolt achieved overwhelming capabilities by solving every problem through application of superior materials, abundant power, and robust construction. These were expensive aircraft, consuming resources in quantities Japan simply did not possess, but they kept pilots alive and won battles through systematic application of material advantage. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.